Thank you. Can you hear me?
Yes.
Yep. Very good. Yeah, very good. Yeah, so before I jump into this talk, I just like to mention something. I really like this conference, but there is like one big problem. Nobody is making a joke. Why? Because I also teach at St. Louis University. We started lecturing, in-person lecturing this week. And with mask, people cannot read your facial expressions, so you cannot make a joke. So in just this week, I made a chemistry joke in class. There was no reaction, right? So in the presentation, I'm going to talk about some of our recent experiments. So we do experiments with electrochemical oscillators. And then one thing that is different from what we did in the past is that we are going to use modular networks. And I'm going to talk about this more. And thank you for the nice introduction by Yuan Zhao and talking about these chimeras. So I don't have to do a lot of introduction about these states. And then before I jump into the talk, I just like to mention the collaborators and some of the previous students' work who I will quickly review. So it's very interesting. My first student was Mahesh Vikramasinghe, and then his job was taken over by Michael Sebek, who is now a postdoc with Laszlo Barabashi, and Jorge Ocampo is here at the conference. He gave a poster. So each of these generation of students discovered a new type of chimera state. So we look forward very much to this amazing theoretical progress on the chimera state. Hopefully the next student comes after Jorge can also kind of discover a new type of chimera state. And then this sort of experiments are very often interpreted with theoreticians, with the help of theoreticians and designed. And then Hiroshi Kori helped us a lot at Tokyo University. And more recently, Chris Bick is helping us with these weak chimera experiments. So I'm a chemist, so we work with chemical oscillators. So after discovery of chemical oscillations, the idea was like, how can we get more complex spatio-temporal structures? And one idea is use some sort of continuous media. This is still very active. Yesterday, I think Markus Hauser gave very nice talk about three-dimensional these waves in a system. But another option could be is taking these chemical oscillators in discrete units. You can think about, for instance, some beaker, and then have some coupling between them and see what is happening. And this was done very early. You can see it's 1975, just a few years after the Kuramoto model was formulated. And then this is this Belousov-Zhabotinsky reaction in a beaker with some mass transport allowed in between. And then look at this, that this is some graphic, this is some recorder, some chart recorder. But they noticed that the two oscillations kind of align with each other. So this is like maybe the earliest paper I found where they showed synchronization in a chemical system. And there were a couple of other papers. And in these very early papers, they already pointed out that the behavior of this, especially the phase dynamics of this system, is very similar to that of the Kuramoto model. So of course, it wasn't analyzed quantitatively, but just on a phenomenological level, they showed a lot of similarities. And then after that, there were like a good decade or two where there were a few very nicely designed experiments on relatively small sets of these tank reactors. And then these kind of experiments were kind of difficult. It was, I think, it was like just a technological challenge. Somehow, chemical engineers didn't develop some very versatile technique to build big networks of chemical oscillators. But I think in the past 1 or 2 decades, there was very good progress in this field. We have microdroplets, Seth Friedan, originally with Irv Epstein, did some very nice experiments. Ken Showalter and Harald Engel have this very nice light feedback modulation with which they can study synchronization patterns in networks of chemical oscillators. And then in this talk, I will kind of talk to you a little bit about electrochemical oscillators. So this is so basically almost all of my slides will be experiments. So this is just it's a very simple experimental setup that you can study electrochemical processes. So I think all the experiments I will show you is with the nickel wire that is immersed in an acid. And then the nickel wire starts to corrode. So what corrosion means, perhaps you are familiar with this with your car and the bikes, that this nickel wire will start to dissolve, that's corrosion. And then electrochemists like to study this behavior very much as a function of some applied potential. They measure the rate of corrosion. So nickel ions dissolve in the solution, so the rate of corrosion can be measured very easily by looking at how much current is going through this wire. And then we can characterize the corrosion quite well if we set a certain potential with respect to some reference electrode, and then we measure the current, the rate of this dissolution. So this is, of course, a huge field. There are big conferences, but from very early on, early 19th century observation pointed out that oscillatory corrosion is possible. So, and then, of course, like with the advent of nonlinear dynamics, we could characterize these nonlinear phenomena. In this nickel dissolution system, we found very nice oscillations that occur close to a Hopf bifurcation, call it smooth oscillations, or they are very close to homoclinic bifurcation. We can call them relaxation oscillators, and we can also have experiments with chaotic oscillators. So most of the experiments I will show you today are with the smooth and a little bit in between the smooth and relaxational region. And then the main bifurcation parameters you can think about is, of course, the potential at which we drive this nickel wire to dissolve. But the other bifurcation parameter very often we like to use is this external resistance, because when the current, you have some current, we have some electrolyte here, there is a potential drop. And then instead of just moving about these wires and the distances of these electrodes, it's a very common technique just to simulate that potential drop with some attached external resistance. So you will see different configurations of these resistances in the different setups, and that's how we can create some sort of networks. So for about 2010, we started to use this device to study coupled oscillators. So in this device, instead of one wire, we put in two wires. So both of these wires can generate some oscillation. So there is what we call individual resistance attached to each wire. And then it's very interesting that if you do not add additional coupling element in this system, these two oscillators are basically independent from each other. This potential drop in this electrolyte is not enough to synchronize the oscillations. And then we can add additional coupling elements. You will see sometimes we use, for instance, cross resistances or cross capacitances to have a coupled oscillatory system. In terms of a theoretical framework, we like to use very much phase models to interpret the results and for designing the experiments. And then these phase models can be actually obtained from direct experiments. And a lot of researchers pointed out early on, I think Ermentrup once said that you can actually look at this phase dynamics directly from experiments. Hiroaki Daido also proposed in an early paper, just as a footnote in a paper, that if you can measure the phase of the oscillations and then you get the time derivative of the phase, then you get the instantaneous frequency. It is the natural frequency plus some sort of coupling functions. And then with some averaging, with the natural frequency of the oscillations are close enough, very often this can be expressed as a function of phase difference between oscillators for each coupling pair. But then if you rearrange the system and then if you put the instantaneous frequency minus the natural frequency that can be obtained without coupling, you plot it as a phase difference, then you can get the shape of this interaction function. And then we know from the Kuramoto model that for oscillations close to Hopf bifurcation, this interaction function is dominated by first harmonic components. It was very interesting when we put this coupling resistance in between these wires, just a very large resistance that just couples the system a little bit. So the instantaneous frequency is fluctuating, goes up and down in time, and the phase difference is of course increasing. We can put the phase difference again in the horizontal axis, this interaction function, this instantaneous frequency minus natural frequency on the vertical axis, then one thing you can see is that it's basically a completely sine curve. And this was very interesting. It was very surprising to us that the phase dynamics can be described by a sinusoidal interaction function in terms of a phase model. Kuramoto himself, when we started working on this model, he obtained a lot of criticism from physicists saying that why you take only first harmonics? This interaction function must be extremely complicated. So what kind of experimental system or what kind of real natural process could generate some perfectly sinusoidal interaction function? And then you can see that there are some examples, perhaps they are very rare, and we don't really know actually why it's purely sinusoidal, why we don't have cosine terms, some phase frustration kind of in this interaction function. But with this resistance, we certainly have this curve, and then we can tune the amplitude of this with the different resistance that we put in. And then it was very interesting in this, we did these experiments with the capacitance, and the idea was that the capacitance delays the coupling signal by 90 degrees or pi over 2. And then it makes sense, we worked with Hiroshi Kori, and then he kind of predicted that this interaction function should also be predicted by pi over 2. So we should get a sort of a cosine curve. And then because the interaction function, the type of coupling that occurs here is through the electrode potential differences. If the electrode potentials are the same, there should be no effect on the dynamics. You can see both interaction functions has a value of 0 at 0 phase difference. So, but the nice thing now is that we can combine the resistance and the capacitance, and then we can basically engineer in the system any kind of interaction function. If we see some sort of theoretical work that use the interaction function with a certain interaction function with some sine or cosine component, we can easily tune up with actually the product of the resistance and the capacitance. We can determine that, what kind of delays that will generate some sort of interaction function. So we did a lot of experiments with 2 oscillators, or with Jack Hudson in the past with globally coupled oscillators. So the next step was what kind of phenomena we should look at for a network of coupled oscillators. So one research direction for us was looking at some interesting patterns that, like coupled, let's say 2 oscillators are synchronized and the globally coupled oscillators are synchronized, but with some sort of network, we'll generate some sort of interesting pattern. So that's why we were very much interested in this Chimera pattern, and for this original papers by this Kuramoto Chimera, we talked and consulted with Oleg and then also the Japanese collaborator, what type of networks we can build. That is, of course, we have these cross resistances. We wanted to look at a relatively small network. So we looked at some sort of small network, and one of the smallest network that was feasible in the experiments that was this 20 ring. And then each of the element is coupled to 7 of its neighbors on the right, 7 of its neighbors on the left. And then for this observing this chimera state where this symmetry breaking when a part of the elements are synchronized and the others are not, we wanted to make these oscillations extremely similar to each other. So this can be adjusted by the system parameters, like just tuning very finely their frequencies. So in this case, the frequency of the oscillations was about ±1 millihertz, and the natural frequency is 400 millihertz. So these are extremely similar oscillations. And then we picked this, this network. And then we added the coupling, and we kind of see this kind of chimera state. So let's look at here first the frequency of the element as a function of electrode number on the ring. And then without any coupling, you can see that they are basically identical. So these are extremely similar oscillators. If we initiate a phase profile for like hundreds of cycles, that phase profile remains there. So without any coupling, we really don't see any change in the relative phase distribution. But once we couple the system, of course, it was not so surprising that some of the oscillators synchronized, but what was very shocking to see that these oscillations, some of the oscillators become desynchronized. You can see compared to the natural frequencies, they have very, very different frequencies. So just to, this is like a phase minus mean field phase for the different electrodes. You can see this electrode 1, 2, 3, 4. They are all just nicely synchronized. And as you go away from this core, Chimera core, you get one phase slip here. This is the phase difference, right? And then 2, 3, 4, and that generates this sort of semicircle in the frequency. Just to give you, I don't know if you can see this graph. I think this video is very fast. I just give you some snapshots here. So these are the elements that are synchronized. This is the current actually that we can measure. And you can see that these other elements here, this is different, but another element, this is other time, this is synchronized and this is different. And another, let me try to get maybe another height. You can see these are similar, but these become very different. So this is very interesting to see. But what is kind of plotted here, we could only observe this as a transient. This state, this is the only, this 200 seconds, this was a transient, that after this 200 seconds, the system very quickly converts to a completely synchronized state.
Istvan, it seems that your screen has shrunk.
Yes. Now it came back, coming back, right? Yes,
okay.
Very good. Yes, because a movie I couldn't control in
I
full
see.
screen.
Okay.
So, and then, we stopped these experiments because we saw this Chimera only for 100 cycles, and then we had to adjust the frequencies. So we just decided that this type of Chimera in our system is just too fragile. It was very difficult to observe. So we still kept an eye on the literature, and then it was very excited about Pete Ashwin's nice paper about this weak Chimera state. It is part of this effort of looking at higher harmonics. Maybe if you introduce higher harmonics in the interaction functions, these chimeras can become more prevalent and more robust. And and then this is basically what they found, and they gave us also this very nice definition of what a chimera should be. A weak chimera is that if you have like 3 connected nodes, 2 of them have the same frequency, 1 of them is different. And I think on the next slide, I kind of explain it better, is that some of the simplest system is that you take 2 groups of 2 elements, and then you have strong coupling within each of these populations, and then you have some weak coupling across the populations. And if you introduce some higher harmonics in the interaction functions, so you have now sine 2 component, and of course we also need some sort of phase shift, some sort of cosine component. Then what can happen if, let's assume there is no cross coupling here, so epsilon is 0, then it is possible to get bistability between in-phase synchronized and anti-phase synchronized system, and then those 2 oscillators have different frequencies. So when we increase the coupling strength, this state is very robust. So that was a prediction based on some phase model simulations. So the question was, can we find some experimental system that can show this sort of behavior? And then we managed to find such first with this feedback system. So in this case, the coupling is not through this coupling resistances and capacitances, but each of these wires, we can change a parameter, the circuit potential of the system, and then we can take an average, we draw a graph, and then we just combine all the currents from the neighboring electrodes and then feedback that value to that node. So this is kind of this virtual kind of network. And then we can introduce delays. And so it is, the question was, what kind of feedback we have to design to get this interaction function. And unfortunately, we solved this problem with Hiroshi Kori in 2007 with this synchronization engineering technique. And the idea was relatively simple, is that linear feedback for a nearly harmonic waveform oscillation generates sinusoidal interaction, first harmonic interactions, and then quadratic feedbacks can generate second harmonics as well. And then all we have to kind of optimize is this feedback gains and different delays to get this combination of first and second harmonics. And then in this new work, we actually did a little bit of progress on how to even better engineer these interaction functions, that instead of direct feedbacks, we use different types of feedbacks that just makes the fitting so much easier. Basically, there is no fitting. You can see here a lot of parameters, but I think just very quickly show it's basically everything is zero in that feedback. The only thing that we have that is non-zero is this, we have a linear, we have to decide just the ratio of the linear and the second order feedback, right? And that basically tells you the balance between the first and second harmonics. Then we could measure this interaction function like we did before. I think this black curve was the theoretically predicted interaction function that can generate chimeras. And then this red one, that's what we observed experiment. You can see it's not identical. There are always like higher harmonics. And then once you apply this feedback to this system, we got very nice, extremely robust chimeras. So these are very different types of chimeras than what we had before. Again, let me just go back and show you this movie here. So we have these two elements are in phase. As time goes on, they just remains in phase. So we have a co-rotating frame of reference. And then these other elements, we start them from nearly anti-phase, and then they remain anti-phase. So that phase difference is close to pi. And then as you can see, this 1 and 2 cluster state, even with some cross coupling, they have different frequencies. Then they generate these V chimera states. So of course, this was with a feedback system. And then when Jorge came, he has we started to pose the question whether, yeah, let me just make sure, whether such quick chimera state can be observed in an actual device, not with this feedback. And then of course we know a lot of this, the nonlinear dynamics of these systems, but what Jorge started to build is this new modular network. So now we take the metal wires and then we can create one module by coupling them to what we call a group resistance. And then we can get another group of wires. This is like 14 one, 14 the other, another group resistance. And then we can have some coupling between the two groups by adding what we call collective resistors. And then we can use Kirchhoff laws, and then we can calculate the electrical coupling strength within the population, and then in between the population, so we know this coupling strength, and then know how to tune this coupling strength between the population. So the question was how to find these conditions where you have the coexistence between this 1 cluster and 2 cluster state with different frequency. And then we found some conditions in the past when we were looking at different interaction functions as we changed one of the bifurcation parameters in the system. So in this case, we were going away from the Hopf bifurcation and approaching a homoclinic bifurcation. And then in between, we found this interaction function that you can see here. It has kind of two humps, and then there are also cosine terms in it. So, and then this is just some old result that if you take a globally coupled population, you had 1 cluster state and 2 cluster state coexisting, depending on initial conditions. But we never measured their frequencies. So when Jorge came in, the first
you
thing
have
he did,
2 more minutes.
Oh, very good. Yeah, so we had these two groups. So this is with global coupling. And then we could manage to confirm that they have different frequencies. This is the 1 cluster state. Let's say this is the 2 cluster state. And then when we put them into this population of oscillators with some cross coupling, we observed exactly these two types of this chimera that we have seen before. And then there is a final thing I just like to say. We had some theoretical explanation for this, but like what is the difference between these 3 different types of chimera state? So the original Kuramoto chimera state was close to Hopf bifurcation, and then we had linear coupling, linear interactions in terms of the physical variables, and they were coupled with delay, and they were on this ring. We found that this chimera state was very fragile. And then we looked at this, and then we looked at this weak chimera state, which was obtained with highly nonlinear interaction of weakly nonlinear oscillators. So we used very nonlinear interactions to intensify the nonlinearity of the system. And then this more latest results, we went back to linear interactions, but strongly nonlinear oscillators. So you can see that, combination of these different effects, we can get these different types of chimera states. Yeah, thank you very much.
Thank you. Thank you very much, Istvan. Again, we are tight in time. Maybe one short question. I don't see a question in the Q&A section, but maybe you have presented your a state where you have two oscillators in antiphase and two oscillators are incoherent. So it's kind of antipodal state. Did you ever observe a double antipodal state in the sense that you have two pairs in antiphase and another pair in antiphase, but with a different angle, different phase?
Yes, we have not seen such state yet.
Yeah.
But like we have something else that is maybe like a little bit different, is that you can take oscillators in basically the same network that normally would synchronize in phase, but in this network, they synchronize anti-phase.
Yes, but the double antipodal, we found that theoretically in adaptive networks, but there it's unstable. So it would be interesting if you have any situation where where you observe it in a stable way. But
but the phase angle is different, right? The phase angle between
so we have one antipodal pair and another antipodal pair with a different angle relative to the first pair.
Yeah, we have not seen this.
Okay, so now I see one question. This is by Rico Berner. Do you see a possibility to make the coupling weights between oscillators adaptive to the dynamics of the oscillators? Weak chimera-like dynamics has been also found for adaptive networks.
Yeah, so like in terms of a device, we were looking for it and we were very carefully measuring this sort of coupling strengths, in other configurations. But we have not found such a state yet. Maybe we have some states where there is different state depending on the state of the system. You could have low or high coupling, like some part of the cycle, the coupling is weaker, another part of the cycle, the coupling is higher. But yeah, we have not seen, in electrochemical devices, we have not seen this coupling strength changing much.